In this episode,
yeah, it's 35 mil, 28 mil for each floor, and then 22 and 15 as required.
Are you fitting with Wiesmann by any chance?
Your percentage of error is huge at 5 degrees. It's not very big at 20 degrees.
They might have left a bit of snot of solder in an elbow.
If you're still not getting hot and you've got everything turned off, then I think you need a new pump.
You're losing nearly 1 meter of pressure per meter.
It's a challenge. It's another block.
and welcome back to another award-winning episode of Homeowners Q&A. I'm your host Mars, and today we're diving into a topic that doesn't get anywhere near enough attention, and that can make or break a heat pump installation: poor pipe sizing. To explore this, I'm joined by Mark Hall from SMH, Mark Parker from Elite Renewables, and Brendon Uys from Hall. Welcome, guys. Before we begin, we'd like to thank our sponsor, Elite Renewables, for making this episode possible. Elite Renewables are helping London and the South East with heat pump, solar, battery and MVHR installations. They've installed thousands of heat pumps over the last 20 years and work on projects from new builds to tricky renovations and retrofits. Their Croydon office and showroom is fully sustainable, being heated and cooled with a ground source heat pump, so feel free to pop along and see the technology in action and meet the team. If you're considering a heat pump installation, get an estimate from eliterenewables.co.uk or check out their YouTube channel to see behind the scenes of some of their projects. Thanks again to Elite Renewables for supporting this conversation. Brendon, do you want to get us going today? When it comes to low temperature heating like heat pumps, why is pipework and pipe sizing so important?
Heat pumps and boilers require different flow within the system to operate at best efficiency points. A gas boiler or an oil boiler, you require between 15 and 20 degrees difference between the flow and the return temperatures for optimal performance of that boiler. A heat pump is completely different. It requires approximately 5 degrees between the flow and the return temperature to operate properly. It's got to do with the gas circuits within the heat pump. Outside those areas, it starts deteriorating in performance. Not all heat pumps are exactly the same, but in general, it's around about 5 degrees. When you look at that and the actual amount of water flowing through the system and calculate it out, that means a heat pump requires 4 times the flow rate of a gas boiler or an oil boiler to achieve the same goal. What we are doing is we are heating properties with water. We are moving heat with water. It is the medium that we move the heat into the property. If we don't have enough water flowing within the system, we are not moving the heat. If we aren't moving the heat, the house will be cold. It's really as simple as that. So when you are designing a system, you need to make sure that your pumps have adequate pressure and flow available to them to actually move the heat into the property that you require to heat that property. It's all very well doing all your heat loss calculations and everything else and sizing the unit outside, and then your pipes are too small and you just can't get the heat into the property. You might as well have just missed out another stage along the line, and it won't make any difference. It is a complete package when you're designing a heating system with a heat pump, and it's very much more critical that it's done correctly.
So, Mark Hall, the last time I saw you, we were both hanging out with Freddie Lundberg at Installer Show, kind of a bit of a name drop there. I also know that you are working on actually refurbing your home at the moment. So how much emphasis have you put on actually getting the pipework size or the pipework sizing correct for your property?
Yeah, it was pretty critical here because a little overview of my system. It's I wanted to do it open loop. I was speaking to Brendon before about the fact that I didn't quite have a residual head figure given by the manufacturer. Basically, sizing each pipe to every radiator was critical to get the heat to every room. My index circuit, which is the furthest or hardest to heat radiator in my circumstance, I had to kind of work out backwards that I would have enough head from my pump to get to my furthest away radiator. So it's a 250 meter squared house. So there's 23 radiators and I wanted to run it off one pump. And as Brendon said, you need 4 times the flow of a gas condensing system. So you've got DT5, not DT20. So mass flow rate heat loss, heat load, pipe sizing, velocity and resistance are all these things you have to consider if you want to heat every room, including that last hardest to heat room. So apart from the practicalities of getting through a 300-year-old house with joists that are small and pipes that are potentially big, I had to kind of reverse engineer it. And one thing I did do was split the load between upstairs and downstairs. And when we get into the nitty gritty of it, you can see why that helps in terms of pipe sizing and sharing the load, sharing the flow, reducing the resistance. There's things that we learn and everything is related. So if I didn't want to think about it or do any calculations, then I could just put a buffer in and a second pump and it would do it. And I would lose efficiency. And I didn't want to do that at my house.
So did you actually go and pull out and replace all of the pipework, or did you actually end up reusing what was there already?
Yeah, well, interestingly, we talked about 4 times the flow of a condensing boiler. When the original heating system was put in, it was put in for probably DT11, so somewhere in between. So actually, a lot of the pipework was of good size, but I've ripped it out and started again because it was in the wrong place. I switched the heat source from one end of the house to the other, and also it was full of black sludge. So I'm not going to put that on, so I just started again. And that's with a refurb, you can calculate every pipe run. And I've gone through some joists because practicalities of actually putting larger pipe through smaller joists with older houses is an issue. So I've had to work with a route that in some places that was already there, notched out joists. They are all new pipes, so I could calculate every pipe to every radiator.
So Mark Parker, not everybody is in the same kind of situation as Mark is, that, he has had the opportunity to be able to replace all his pipes. I'm sure a lot of the properties that you guys are going into and refurbing are going to have existing pipework that homeowners just couldn't be bothered about ripping off drywalls and, replacing that. What is the way to actually get around that, if you don't actually know what kind of pipes are behind that wall? How do you get around that to actually make that system still run efficiently?
Yeah, it's always a tricky one. As sort of Brendan says, it starts with your heat loss survey. You have to understand what heat you need to deliver first. If you know what that is, you can work out the flow rate of the system. Usually start with a heat loss survey, the full building, you know what you need. You can then work out your primary pipe work from the heat pump to the if you're doing it to the plant room, and then where that split off basically happens. That's the crucial side for me, is getting that part done right. And then the next side is then figuring out, okay, looking at each radiator, having a look at what pipe's coming off the radiator. I mean, it's all very well and good saying, it's 15 mil pipe on the radiators, but you can't take up every single floorboard and have a look. So you've got to make some certain assumptions in some situations, and you just have to be clear with the homeowner that potentially it could be a risk. But if you've done your research, you've done everything you can to find out what pipe is at point A, what pipe is at point B, you can then make a good assumption that actually, the pipe in between, they should be 22 mil, should be 28, whatever you've seen. So once you know what each room needs, you can identify what each pipe to that room size needs to be as well. And it just comes down to a flow rate and pressure equation that you do. You can look at flow charts and all sorts of things. I think this is something that in the industry is just not done enough. And I think for people like us who know what we're looking at, because we've done this so many times now, it's easy. But for someone who's just moving on to heat pumps from boilers, it can be a bit of a nightmare. It's not checked enough. So yeah, that's my sort of thoughts on it.
So you mentioned that the primary, so this was actually one of the questions I was going to ask, but it's a good time to do that. So I think a lot of installers recommend running 28 mil primaries basically into your system. But what I can't get my head around, and I'm not a plumber, and I really cannot understand how these things work, but if you've got a 28 mil primary that comes in, for example, and that funnels down into a smaller pipe, surely you're still creating bottlenecks somewhere down the line?
Let's say you've got a 7 kilowatt heat pump and you've worked out that the primary pipe work needs to be 28 mil. Fine, that's all well and good. As long as it splits off from that 28 mil pipe, you've got 22. If you know what heat load is going down that side, what heat load is going down that side, you can work out the 22 should be okay. It just depends on the heat loads. You can go to literally, as Mark Hall's doing, you have to, because you're doing open loop, you have to check every single pipe in the house. Otherwise, it won't get to that radiator if it's too small diameter. or if the distance too long. So you can make a pretty good educated guess based on what you can see. But 28 mil is generally fine. Depends on your heat loss, of course. But if it's a 7 kilowatt heat pump, it generally is 28 mil. But if it's anything over sort of 10 kilowatt, 12 kilowatt, then you can go into 35 mil. It just depends on the pressure loss and the flow rate down that pipe.
It's critical that when designing a system, you actually know what pump head is available to you. Some pumps on the market some heat pumps on the market are phenomenal. They have masses of head available to you. So it's never a problem. You can put a 12 kilowatt heat pump on a 28 mil pipe and it's absolutely fine. But others, like Marco was saying just now for his system, he had only 2 meters available, which is very, very small and very tight. So the pipe sizes have to go up to prevent the losses so that little 2 meters will be available to you.
The only problem with that, Brendan, so even if you've got a massive head on the actual pump, on the heat pump, if you hydraulically separate that system, that kind of doesn't make a difference, right?
Yes, exactly. If you hydraulically separate the system, then you are looking at two different circuits. You're not looking at one circuit. There's a circuit for the heat pump and there's a circuit for the house. When you are designing the system, you have to know what water is actually moving within the system. If you don't have proper flow meters and equipment to actually test the flow, then you're just guessing. And that's part of the reason why system separation has such a big problem, is because you're just guessing what's happening on the house side. In 99% of the time, you have absolutely no idea what's happening there. And are you moving the right amount of heat? The heat pump's probably producing the right amount. It's producing more than enough. But are you actually moving that into the house? Nobody knows. And that's where the problem comes. As Mark was saying, that when you come to retrofit scenarios, we really don't know what we're looking for. We don't know what we're looking at. I've come across, and I'm sure we've all come across, some horrendous situations. One of the worst I came across was a house where it was 28 mil going into the garage, from the garage into the house, and across the bathroom, on the other side of the bathroom, was 28 mil. We lifted the floor. Everything looks great until we fired up the heat pump and it didn't work. Couldn't get the flow rate. Turns out that there was 15 millimeter pipe under the bathroom. Because of some reason, they hadn't done that. It worked all right with the boiler, but just would not work with the heat pump. In general, on retrofit, if you've got enough flow and pressure available from the pump, most existing pipework will be adequate for a heat pump. You can add other pumps. It's a lot cheaper. And if you look at economies of scale, it's over a long period of time, even with the extra pump, as long as you're controlling it correctly, it's still better to put an extra pump and not totally destroy the house.
So Mark, you're in a great situation where, you're doing everything from scratch. So just walk us through kind of the various pipe sizing that you've gone through. So from your primaries to, everything else that kind of splinters and runs through your house. What did you go with and what was your thinking behind that?
Again, it all starts from a heat loss, so what heat you required, and mine is about 12, 13 kilowatts. I can't quite remember, but it's between 12 and 13 kilowatts. So as other Mark said there, that you've got an option of pipes there, 28 or 35. Both will deliver the flow down that pipe, but then you've got, if you choose 28 mil pipe for my load, then you're going to have a lot of resistance per meter and per bend, and that's going to add up all the pipe between there and my index circuit, my furthest rad. All that resistance is going to add up. So I decided to go 35 mil. So you got 4 options of pipe in your heating system, really, from 15, 22, 28 or 35. So 35 was ideal because you've got to make sure the flow goes down it, try and keep your resistance down, but also you've got to keep within a range of velocity. So we hear this 0.9 meters per second is kind of the target, but you've got a range of, say, 0.4 to 1.5. So if I put it down, a load down to 22 mil pipe, it might still get the flow down there, but the resistance might be extraordinary. You use up your pump head straight away. There's too much. It's too difficult to push that amount of flow down that pipe. So you put the same flow down a small pipe, the velocity increases, you can get erosion and noise. So you have to be aware of resistance, velocity and flow, and that all comes from your initial load. So Mine was 35 mil, and then I almost immediately split. And because I've got suspended floors upstairs and downstairs, I could split my upstairs and downstairs load. So I could almost hit, not quite exactly half, but half my heat loss is now downstairs, and let's say half is upstairs. So then I need to get half the flow down this circuit and half the flow down that one. So that means I can immediately go to 28 mil. And then each section, because when I do downstairs, say I've got 6 kilowatts of heat load to get down that 28 mil pipe, well, then a rad might come off. And I've sized that for 15 mil, then another one. And then suddenly it needs to get 4 kilowatts past that section of the pipework. So then you start to reduce down, or can reduce down, without affecting velocity, resistance, flow, that kind of thing. So it's a step-by-step approach, and each bit of pipe has got a certain amount of energy, a certain amount of heat it's got to get down it. And once you take a radiator away and another one, it's got to do less work. So that's why you don't have 35 mil all the way to the end radiator, because your velocity would drop. It's unnecessary, all that kind of stuff. So yeah, it's 35 mil, 28 mil for each floor, and then 22 and 15 as required.
Are you fitting with Eastman by any chance?
Yeah, it's already in. Yeah.
You said indoor units. No, they're good bits of kit because of they're doing it slightly different to other people as well with their it's the internal buffer vessel, so it's makes it a bit easier as well for defrost and stuff like that.
One of my main reasons for going for the Wiesmann unit is I was lucky enough to have space in the cellar for an indoor unit. A lot of people don't.
Yeah, they're big units, to be fair.
Yeah, that's right. Yeah, but if you've got the space, I think the SB full-way valve and the indoor unit and the internal buffer just for defrost just eliminates a lot of defrost issues that a lot of other manufacturers can have.
What Mark Hall was saying there was, as the pipe goes down the line, you're tapping off 2 different radiators, and the flow rate down your main primary reduces as it goes down. The disadvantage of that is that the friction loss to those closer radiators is very much lower than the friction loss to your furthest radiator. Once you've done that design, the critical part of that is actually balancing the system once it's running, to make sure that each radiator, again, is receiving exactly the right amount of water or flow that is required for that radiator to distribute the heat that it is designed to do. If that radiator, say, requires 1.5 liters a minute to distribute the heat, if you're supplying it with 0.75 liters a minute, that radiator is half its size. You've reduced that radiator by half the size, and that room will be cold. Not because the radiator is too small, not because the pipework's wrong, not because the design is wrong, because the commissioning has not been done correctly, and the exact right amount of water is not being delivered to that radiator, that specific radiator throughout the house.
Yeah, it's a really critical point that Brendan's made, because water does want to flow down the easiest route. So it goes down that 28 mil pipe, and that first radiator is there, and your furthest radiator downstairs is 10 meters away. It will just flow around that one, and you won't share the flow, although everything has been sized properly. So you balance down the flow on the radiator to kind of equalize. You want it to almost, you've got to be careful of doing it too much, but you want to equalize the flow almost to, well, the flow that is required for each radiator, but you want to almost match the index circuit. So when it goes down, it's squeezing a little bit past that first radiator, so it's still got lots to go where at the other part of the system it needs to go to. So yeah, that balancing part is critical. It is less of an issue, I think, with DT5, isn't it? Because the flow and return temperatures are similar. Would it be, you've got to get the flow right?
It's more critical because your flow is much greater. That first radiator, or the first few radiators in the line, the friction loss on those radiators is very much smaller, so they will take the greater flow.
The classic example is a builder putting in an extension and just whacking a radiator on the end of the circuit and not not rebalancing the whole system, and then all of a sudden the radiator's not working in the winter.
How critical is kind of radiator balancing? Because I think a lot of people just kind of tend to forget about it. They go and have a fiddle. One room gets a little bit cold. One room gets a little bit warmer. That they mess around with the lock shield, and before you know it, the whole system's kind of gone a little bit pear-shaped. So just how critical is that, Mark Hall?
Yeah, it's funny because there's a new product on the market I've seen. Have you seen the flow setter lock shield valves for radiators?
The FRV.
Yeah, that's right. So, yeah, interesting. I'd like to see what the other guys think about that. But because you've designed the system and each radiator needs a certain amount of flow. So, yes, you need to balance it so it's all equalized. The thing is with balancing, and the reason a lot of engineers don't do it is because it can take a long time. These flow lock shields that we're talking about that have just come out, they give you a visual indication of what the flow is. So you, in theory, you could match that flow, that visual flow, to what you've designed it to at -3, let's say. So other parts of the year, it might not be relevant, that flow, because you need less flow in different temperatures outside. So that's one thing why balance is difficult, because you want to be there on the coldest day of the year. You need temperature clamps, essentially, on every pipe if you want to do it right. Set the flow to what you've designed to. So, yeah, it is difficult, and it might require multiple visits. That's why, like you say, this is a bit cold, that's a bit warm. You do it, and then you'd have to let it cool down again, let it heat up again, and then, and we're talking lower temperatures with heat pumps. With boilers, you can whack it up to 80, and you can kind of... so it is a challenge. I mean, if you have a customer that knows how to balance the system in terms of touch and temperature in rooms, they might be able to do it at a later date. Otherwise, it could involve multiple visits. How do you price for that?
Problem is, they might want to install the system themselves if they know how to do that.
Good luck. Yeah. Good luck.
The other problem there is the difference between balancing a heat pump and a boiler system is that most of our heat pumps on the market are dynamic, both in flow rate and in capacity. When you start closing radiators down, the heat pump will just speed up, and you'd open it up and it'll slow itself down. And because it's dynamic, it's changing all the time. So you don't have a static point to work from. The other thing is at 5 degree delta T, it's a very difficult thing to balance, because a lot of your temperature sensors can be 1-2 degrees out. Your percentage of error is huge at 5 degrees. It's not very big at 20 degrees. So balancing at 20 degrees is not such a difficult task. Number one, generally the boiler has a fixed output. You can wind it up, let it run. And if you're 2 or 3 or 4 degrees out between radiators, you're still pretty much there. But you be 2, 3, 4 degrees out at 5 degrees, you're way out. And that's where the big problem is. It looks like that little valve might solve a lot of problems.
Are you thinking about getting a heat pump? Then don't get caught out by a bad installation. Bodge Buster is your essential guide to asking the right questions and spotting red flags before it's too late. Written from real homeowner experience, this book gives you the knowledge to avoid costly mistakes and make informed decisions. Get Bodge Buster today in print or for Kindle, link in the description. So Brendon, I know you're not particularly big on buffer tanks, but is this the reason that a lot of installers are putting them in? Because it removes a lot of that issue from the equation when it comes to balancing. You said that the heat pump's dynamic, it kind of gears up, gears down. Is that why they're putting these things, just so they don't have that headache?
I don't think it occurs to them on that side of it. The buffers are mainly put in to protect the heat pump, the flow of the heat on the heat pump side. The secondary side is generally forgotten. They just chuck a pump on there and hope it works.
The problem with the industry and manufacturers as well is when they first started coming out, they recommend putting buffers in to protect. It's just the way they wanted to do it is not necessarily the best for the house. They've changed their stance now, especially for people like Valent and stuff. But the initial schematics, they always wanted the buffer. They always wanted hydraulic separation. And then you just lead to problems.
The Valent unit is not so bad with a buffer because it's got a fixed flow rate. It's not dynamic. And that can have serious disadvantages because it means that your 5 degree delta T is not fixed. On that Valent unit, the delta T, depending on the design, can range from 1 to 10, depending on the capacity, the time of year, how far the heat pump's modulated down. It's a very, very good unit, but because it hasn't got the delta T and is not controlling the system exceptionally well, it tends to be one of the better units on a buffer tank, put it that way. If the other side of the buffer is controlled and has got the correct flow rate, and the flow, because that flow rate is static, if you have roughly a static flow rate on the other side of the buffer, then you don't get the distortion within the buffer.
So, Mark B, how much emphasis do you guys put on actually balancing the radiators when it comes to kind of the end of the project? How much emphasis do you actually place on that?
Yeah, as Mark Hall says, is you can balance it to a certain degree, but usually when it starts to get colder, we often go back to the house and just redo it or make some amendments to try and optimize the system a little bit better. It depends on a few different things, but yeah, you can only do what you can do in the situation and at that time. So it's just a case of we let the client know, let them know exactly what the reason is and why we need to potentially come back, and they're okay with that, most of them.
So would you guys consider fitting things like these little flow regulator valves? Would you guys consider doing those?
Well, the thing is, it's probably going to cost us more, but the fact that we don't have to go back to that house and revisit, and we actually will probably save money doing it because we're not revisiting, and that's probably the same for most installers. And it also eliminates the problem of an installer that's maybe inexperienced, who doesn't know how to do these things. It gives them a better fighting chance to get the system balanced correctly if they've done all pipework sizing correctly and all the heat loss survey and everything. So it's a combination of all these things that need to all come together and work, seamlessly.
Mark, you brought up a very good point, is the new installers coming onto the market are inexperienced as to how the system should work. By putting these FRVs in, that will give the correct flow rate to every single radiator. And it'll be very evident very quickly whether the pipework is too small or undersized. I think it's going to help the industry quite a lot because there's more. It's a better tool to actually determine whether those radiators are going to get the right flow rate. It's not the end of the world if they don't have the right flow rate. They can put another pump on and just operate it on a proportional load control, which most pumps have. It's the curve that goes upwards from the bottom left to the right, and that follows it'll follow the heat pump and just boost what the heat pump is doing. That will make a very big difference to general installations and probably in the mass market installations as well, where less care is generally put into the installations. As long as that balancing is done correctly at the end of the day, got a very good chance that everything beforehand is going to work all right.
Yeah, sometimes. Yeah. I think it will help a lot. It's just, as we say, that the new installers, they need to get the legwork done prior. They need to know what those flow rates are as well. And that's often the problem, is they just don't know.
I've actually seen the box. On the actual box, it tells you how to work it out. And there's a little table and the chart is really simple.
Yeah, if they do it.
Yeah.
So are solutions like this, would they help? Because we had our installers come back multiple times to try and rebalance our rads, and it was just an absolute fiasco. They just couldn't get it right. They were saying that we've got variable kind of pipe widths running to the north end of the house, to the south end of the house. It was all kind of splintering out. They just couldn't get their heads around it. So would devices like this then ultimately just completely balance the system fully, Brendon? So, if you've got 12 radiators or 20 plus like Mark's got, would it balance all of them?
As long as you've got enough pump pressure and flow rate, yes. That's what I said earlier, is that when you are balancing the system, if you haven't done your maths right, or there's a hidden problem under the floor that is just have no ideas there, it will make it evident that there is a problem, and you shouldn't leave it there. No installer should leave it there. They must sort that problem out, either increase the pipework or increase the pump flow rate and pressure. It's a problem that needs to be sorted out. It can't be left. It can't just be, oh, well, that's that. There's nothing I can do about it. That's not acceptable in any industry.
Thing is, you can put a bigger pump in, which is less efficient, but at least your house is going to be warm. That's the critical thing.
So, Mark Hall, I think the one thing that gives a lot of homeowners that are thinking about putting heat pumps in kind of cold sweats is microbore. Oh, how does one get around a property that is predominantly microbore?
If you can establish the length of, let's say, 8 mil, you're going to struggle with. If you can determine the length of 10 mil, so where it comes from the radiator and where it connects to a bigger pipe, and also you've got to counteract flow and return, you can calculate it. So the point is there's no, yes, it won't work, no, it won't work. For that length of pipe, you can work out what load it is, the velocity, the resistance to flow, is it on index circuit, all these kind of things. So the answer is it can be calculated. So there is no yes or no. What you might find is because you've got so much 10 mil and that resistance for that section is so high, actually you've almost eaten up your residual head of your pump. So then you might be into the realms of it needs another pump. So you have your primary pump into a buffer, then another pump. Not where you want to go, I would suggest. Really, your first port of call is open loop, and hopefully that one pump can get the flow through those pipes. If it can't, you've got two options really. You've got to add pump power, or you've got to repipe that radiator. It's mathematics, it's physics, it's getting flow down pipes. So it's got to be worked out. The other variables you don't know is how blocked up are those small pipes. So we base our calculations on a pipe diameter. Well, if it's 10 mil and then it's got 1 mil of corrosion, it doesn't sound a lot, that's stuck on the inside. Also, how have they bent it? Have they kinked it? So retro is very difficult when it comes towards microbore. I'm sorry to say, if you're a homeowner and you've got it, but it's difficult.
Not a problem.
Why is that, Brendan? Why is it not a problem?
No, it's not a problem. It is a problem, but it's a problem that can be overcome. Let's just, as Mark was saying, at pump pressure, and let's put a couple of figures to this so that people actually realize what sort of problem microbore can be. An 8mm microbore pipe at a velocity of about 1.5 meters a second will give you around about 3.8 liters a minute, which will give you about 1.3 kilowatts, somewhere around there. That'll heat about a 25 square meter room. The big kicker here is to get that amount of water through that 8mm microbore pipe, you're losing nearly 1 meter of pressure per meter of pipe. So Mark's system, where he's only got 2 meters available to him, he could only put in 2 meters of microbore before he's got no more pressure available to him whatsoever. And that's it, his system's failed. And that is the actual implications of it. It is that critical, and that's why it so often fails. What you can do, as Mark said, put a buffer. You can actually quite happily put a pump in series. They work. There's absolutely no reason why you can't put a pump in series, so you can boost the pressure. But again, you need to make sure that you're not over pressurizing the system. It will cost you more to run. That is an inevitable fact because you're delivering more pressure to achieve that same job. That pressure costs money. But is it going to cost more to run over the next 10 or 15 years than ripping out the entire system and starting again? Possibly not, as long as those radiators are sized correctly. The other thing you can do is you can actually push the delta T at duty point. So only when you are at your critical point at -3 or -4, you could push that delta T to 10, which halves the flow rate. At half the flow rate, that pipe effectively is double the size. So now instead of an 8mm, it's actually a 16mm, same as a 15mm pipe. And you get exactly the same pressure. But that's only at the duty point. Your radiators have to be sized to do that, so it's possibly an extra 30% on the radiator sizing. It's got to be designed correctly. It can't be just thrown in. All of this needs to be taken to account when you design the system. Microbore can work. It can work exceptionally well, but it's got to be designed. When you're at 3-4 degrees, which is probably 80% of our heating season, that delta T will come down to 5 because the load is much less, and you're still getting the same water through and everything. It'll work quite fine. It's a trade-off that you've got to do, and it's something that the designer or the installer has to discuss with the customer to make them aware of what the implications are for whatever they do.
Yeah, it's interesting because what Brendan's saying is you can play with the maths, you can widen DTs, and as part of a formula, you can change different parts of it. I mean, you've got to be pretty switched on to do that. And changing from DT5 to DT10, it depends what type of pump you've got, who's in control of it, how it affects the other part of the system. So, yeah, it can be engineered in or out. It's like Brendan says, it's a problem you can solve. It's which way do you go? If it's impractical to pipe it and you've got to get over it, then there are ways around it. I think Brendan's right is that if your customer can understand, you can have a conversation with them. You need to talk to them about it. Part of your podcast, Mars, is trying to give homeowners some knowledge to why yes you can, why you can't, what issues we might have. And at the end of the day, you can engineer it and do the maths and alter things. But at the end of the day, you've got to see whether that room's warm. Have they bent the pipe? It's all theoretical, and the flow is theoretical. They might have left a bit of snot of solder in an elbow, and suddenly that affects it. There's the maths, and it's a challenge. Going open loop and engineering these things in. A lot of the risk is on the engineer to get it right. The benefit is the efficiency for the customer. Put another pump in, put a buffer in. They're going to be warm. It's going to be more expensive to run. You go open loop, you work out every pipe size. The risk is on you. The benefit is the customer. So hopefully you find an engineer that can work with you.
That's not what the customers are paying for.
Exactly.
It's our expertise.
Exactly, yeah.
At the end of the day.
And that's precisely why we feel so wronged with regards to our system, because we've got microbore that runs probably 10 meters that way, 10 meters this way. The whole house is microbored, and at no point in time did any of the installation crew flag this. It was just never a consideration, which is why I find this podcast to be so valuable, because if somebody is watching this and they have got microbore and their installer just goes, well, don't worry about it, we'll deal with it. I think you need to get those answers. Ask them what their strategy is. Ask them how they're going to tackle this microbore, because their solution time and time again was just to put another circulation pump, another circuit. We've got 4 now in our system, and our index circuit still doesn't get to temperature. So Mark P, how do you guys actually deal with microbore when it comes to kind of tricky refurbs?
Yeah, we always have the conversation when we see a microbore in any radiator. We have to have a conversation with the client, because it's not your typical setup. On a boiler, it's absolutely fine. As we've said, it's lower flow rates, so it's not necessarily a problem. But as soon as those flow rates are increasing, you've got potentially an issue on your hands. So what I usually do is find out what that room needs in terms of heat loss, what the radiator that needs to go there, if it needs to be upsized. If I know what the heat loss is, I know what the flow rate is, I can then look at what that pipe is. If it's an 8 mil or 10 mil, whatever it is, I can work out what the pressure or the head loss is on that pipe, and I can have a suitable conversation with the client. It's not something you can generally look at while you're there, and you can give them some advice, but it needs to go through a full design process where you check these things and make sure you've got that head loss accounted for, and it could be the index radiator on the circuit as well. So installers like us, I would imagine, we're looking at that, but some of the other installers, they may not be. So it's worth it for the customer to challenge them, 100%.
That conversation with the client, it might be that, Brendan and other Mark, more experienced with heat pump installations than I am. It does take time. It might take them 2 hours to work out, an hour, half an hour. But it might take 3 hours, and an engineer's got to sit down and work that out, not for his own benefit, but, well, in a way, but mainly for the homeowner to do the right thing. There's an awkward conversation that possibly I got to get paid for that. And that's before you give them a price, because strangely, you can only base the price on when you know what materials you need and what strategy you're going to do. So I know it's frustrating from a homeowner's point of view, is what's the price? What can we do? And you want an answer like that, but sometimes it has to be worked out, and that takes time, and possibly you've got to get paid for that. And if you do it for free, fantastic. If you find an engineer that does that to that level, to the skill, without charging, that's incredible.
It's a challenge in the industry, isn't it, as well? Because I think engineers, they'll price the job, they'll get everything they need to get over to the client. But then when that sort of system, that problem comes up, as you rightly say, that could take someone who's not got as much experience on these things a long time to try and actually figure out, especially if it's not just one radiator. You're absolutely right. Yeah, it's a challenge. It's another block.
So, Brendon, I hope this isn't a very stupid question, but is it possible to go open loop on microbore?
Yes, no problem at all.
No problem at all.
Yeah, it comes down to making sure you've got enough pump pressure, and it's absolutely critical that your balancing is done at the end of the day, because microbore will create bigger friction losses, which make the closer radiators or any radiator that hasn't got microbore basically become a racetrack. And most of the water is just going to flow through that one radiator and nothing else will go through the rest of the system. It's probably more critical to balance well, it's not. It's just as critical to balance every system properly to get every radiator what it needs to deliver. We size heat pumps and the heat pump delivers the correct amount of heat into the property, and then we don't balance the radiators very well. So is that heat pump the correct size anyway? We don't, it's a guess. If the radiator is not balanced properly, it's just not going to work properly because it's not getting the amount of water. And I said at the beginning, we're moving heat with water. You don't have enough water, you're not going to have enough heat. If you've got too much water, you're going to have too much heat. So you're going to get a warm room or a cold room, depending on the water flow going through there. And it totally distorts the design you've done, put all that time and effort to size the correct radiators and everything else, all the pipe work and everything, and then you don't balance it at the end of the day, and you've actually no idea what that radiator is going to deliver. Then you're going back 3, 4, 5 times to warm up cold rooms and cool down warm rooms, which actually costs a lot of money.
Are you new to heat pumps and feeding lost? Then From Zero to Heat Pump Hero helps you understand, operate, and optimize your system. No jargon, just simple practical advice from one homeowner to another. Take control of your heating and save energy. Get your copy now. Link in the description. So Mark H, do I actually understand this correctly? So let's just go through like a house that's got 10 radiators. So you've got radiator 1, which is closest to the heat pump, and you've got radiator 10, which is the index circuit one that's kind of furthest away. So is the problem, if they're not properly balanced, that radiator 1 is basically getting the brunt of the hot heat or the hot water? It's exiting through the lock shield and going back through the return back to the heat pump, while radiator 10 is getting kind of the dregs of kind of the remaining heat, and probably not as much as radiator 1. Is that kind of the reason why you get this imbalance in heat between kind of radiators closest and furthest away from the actual heat pump?
Yeah, I think you've got it, Mark. Because say you've got 6 kilowatt heat load downstairs, and each rad is 6 kilowatts. You should have the same flow rate going to each radiator. Let's just keep it simple for a second. When water goes down that pipe and its first radiator is there, or what needs to go down this really restrictive pathway to the other radiators, loads of flow, as much as it wants to, is going to go to that first radiator in theory. So yes, and balancing is trying to make that more restrictive. If you imagine the furthest index radiator is very restrictive, you're trying to balance that value to the same thing without talking about flow rate required for each emitter. So yeah, water takes the easiest path. So you've got to try and give it a bit of a barrier that way with the lock shield, let's say, to restrict the flow, so a lot of the flow is spread evenly. So in theory, you balance down the first rad, a little bit less the next one, and then the furthest one away potentially is fully open. So it shares the flow rate. Yeah, difficult to achieve, maybe more easy if you've got something that tells you the flow rate, rather than just winding in and out and different valves have different what's called valve authorities. Some are very small and got very small range. Some you've got big range of movement. So a little twist and you've suddenly changed the flow rate a lot. So it is a balancing act.
Pun intended.
Yeah, no pun intended. Yeah, exactly. But you're right. You're trying to balance the flow that each rad needs. With DT5, the temperature between flow and return is closer than, say, a well set up condensing boiler system with a DT of 20. So you can really notice a cold rad on a boiler system, I would say, because forget about flow, but temperature is different. So you could have a 70-degree water flowing really nicely to the closest rad, and then by the time it gets to the last one, you've got no flow, no temperature, and do you know what I mean? So, and it's got to come back the return as well.
Again, coming back to what I said in the first segment, we move heat with water. The problem with the index circuit, the longest radiator, we are restricting the flow, and as Mark H said, the first radiator will get all the flow. So that's going to get all the heat, all the energy. The last radiator is not going to get the energy because the flow rate drops as it goes down. So the flow rate at the last radiator could be very, very small. Therefore, it's just not getting any energy. If it's not getting energy, it can't deliver it to the room. And it's really as simple as that. It comes down to flow.
So if I shut down radiators 1 through 9 and left number 10, the only one open, would that then get the full 45?
Yes.
Okay.
I know what you're saying. It's a difficult concept, but because what Brendan says is the energy, the heat, the required is the way it gets to the radiator is through flow. So the two things are intrinsically linked. So if you don't get the flow, you can't get the heat, the energy, the temperature to the furthest radiator.
You mentioned the flow. You just assumed that if there is enough hot water running through that system, it will ultimately get to each and every single radiator. But I think what you guys are saying, that is, if that heat gets consumed and devoured and basically sent back to the return before it has a chance of getting to the furthest heat emitter, that's where the problems happen.
Yeah, I think if you, like you said, if you had your furthest, hardest to heat radiator fully open and everything else closed, which is essentially what happens on a lot of gas boilers when the TRVs shut off, if that radiator gets hot and performs, you know your index circuit resistance can be overcome by the pump. So that is a useful bit of information. You can then work backwards. So you could do that. You could literally shut everything off, make sure that flow is getting to that last radiator, and then you could literally open up going backwards. This is why pipe sizing is important, because then each radiator itself needs its own proper flow. So it is a challenge, but yes, if your furthest radiator on its own can get warm and perform, you can potentially get there, I would say.
If you're still not getting hot and you've got everything turned off, then I think you need a new pump.
What you forgot to mention there is we have an emitter that pushes heat into the room. So you probably will have 45, or as Mark H said, we might have lost a little bit of temperature down the line through the copper pipe. So we might have 44 or 43 degrees actually getting to that radiator. But because there's not enough flow of water to carry the energy required, that radiator drops that temperature very, very quickly because there's only a little bit of energy. It's designed to push out the heat. It's designed to emit heat. That's exactly, it's doing its job and emitting the heat. Because it is emitting the heat into the room, it feels cold. And that's why it feels cold. It's not because the heat has not got there. There's just not enough heat to heat that radiator up properly because it has emitted that heat into the room already.
Temperature and heat are two different things, aren't they?
Things altogether.
Because the heat is the energy that's taken to the radiator through flow, which is why you need the right pipe sizing. The temperature is one thing, but the heat is the amount of energy that goes there. It's a slightly different concept.
Temperature is just a level. Heat is actually a difference between two temperatures when your flow system. The problem with heat pumps is they are susceptible to temperature, not energy. The energy is the capacity of the unit. The higher the temperature we go with the heat pump, the higher you have to push that temperature, the more it costs to push that temperature. It's literally, we are overcoming the laws of thermodynamics, just like lifting a brick onto a table. You're using energy. You lift that brick higher, it uses more energy to lift that higher. The weight of that brick hasn't changed. It's where you are moving that brick. We are moving heat, and that is the temperature.
I think there's that analogy, isn't there, where you could have a radiator in a room that's 30 degrees and it's 21 degrees in that room and it's -3 outside. And you can have a candle in the middle of the room that's 1,000 degrees, but it's 1,000 degrees, but it's got way less heat.
If you've got any questions about heat pumps, then you need to join the Renewable Heating Hub forums. You can connect with other homeowners, share experiences, and get advice on heat pumps and renewables. Sign up today and be a part of the conversation. Link in the description. So a huge thank you to Mark Parker, Mark Hall and Brendon for bringing the heat and insights today. And a quick thank you to our sponsor, Elite Renewables, for supporting this episode. If you enjoyed this episode, don't forget to subscribe and share it with anyone that's thinking about a heat pump upgrade. And if you're an installer, take this as a nudge to double check your pipework design. Until next time, stay warm, stay green, stay tuned. Goodbye.